Greetings and welcome to another installment of Quant. This is 37 in our basic application series, and this time around we're going to continue on with our exciting summarizing data series with part 9. Now, in this installment, we're going to look at a couple special cases of numerical bivariate relationships, time series and spatial or geospatial. But first order of business, let's take a look at our previous Quant challenge. Now, last time around, we noticed two unusual values of prolific pitcher's height, and a box plot revealed that these are, in fact, potential outliers. Now, question, looking at this scatter plot here, do we suppose there are any potential outliers of our weight attribute? And this is a toughie, to be sure. I would never fault anyone for not being able to reliably pick off an answer like this from the plot, but I would note very simply that it appears that a large proportion of observations fall within a relatively narrow band here across the middle. And it's hard to say what proportion exactly just by looking at the graph, but perhaps 1/2, give or take. And we do know that the narrower the IQR, the interquartile range, the closer together the boundaries for potential outliers. And, well, how about that? There are more potential outliers in prolific pitchers' weight than for height. Kind of interesting. Okay, moving on. Time series. Now, time series plots will be quite familiar to many people, I'm sure, probably because of their popularity in ecology, medicine, finance, and other compelling areas of interest. Just for starters here, I would advise very strongly that any serious data scientist use the following date-time format here. 4-digit year, 2-digit month of year, 2-digit day of month. And if we wish to include a time of day component, it goes 2-digit hour in a 24-hour day, 2-digit minute of hour, 2-digit second of minute. And we may use hyphens here, like we have here, to separate our date components, and colons to separate our time of day components. And we may separate date from time of day with a capital T. And voila, we got an example of ISO 8601 date time format. Now, while ISO, broadly speaking, may not be the most popular format used today, from a data perspective, it is to be regarded, to be sure, as the most practical and useful. Now, of course, date time is relative, since at any moment my date time representation will not be the same as someone across the globe. So we can use a Z, capital Z, at the end to denote an absolute time, namely, here with a capital Z, Coordinated Universal Time, also known as Greenwich Mean Time. Now, it turns out that a date time representation like we have here has two personalities, like a split personality. It can refer both to a duration of time and also a point in time. So, for example, consider the date representation for February 11, 1973. And I think for most people, the natural interpretation would be that this refers to the entire day. But it may also refer to the moment the day started, midnight of February 10th. The contrast is more apparent when we include a time component. Now, typically, if we say noon on Sunday, we are referring to a point in time, like I'll meet you at such and such place at noon. However, this representation can also refer to the 1-hour interval of time that starts at noon. Now, a time series plot, like I said earlier, can be thought of as a special case of a scatter plot. And to illustrate, here we're looking at total number of global confirmed cases of COVID-19 versus day. The time dimension is on the x-axis. Our response, in this example, a count or frequency, goes on the y-axis here. The way this example has been plotted here, notice the ticks on the x-axis, the little ticks down here, correspond to the first day of each month. Now, with a time series, we require our time observations to be evenly spaced, or close to it. In this example, our time interval is 1 day. Now, typically, when we talk about a time series, we have no more than one observation, that is one value of y for each time value. And I say no more than one because we may have missing values, and missing values are undesirable from the standpoint of analysis, but they are acceptable and often unavoidable depending on how our data were collected and or managed or mismanaged. Visually, a time series plot is distinguished from a scatter plot by using line segments here. See the line segments, sometimes solid lines or dashed lines or dotted lines to connect the sequence of points across time. Now, notice that when our response in this plot, our response values are relatively small, like we see out here over towards the left of our time series plot. There was not a lot of relative change from one time measurement to the next, one day to the next. Whereas when our response is relatively large, like we see over to the right of the plot, we see some pretty big jumps from one day to the next, at least comparatively. And this is actually fairly common with many time series, especially when the response is frequency, like we have here. And we also see this in finance, where the response is commonly some monetary value. Now, just like with the scatter plot, one thing to look for is trend. Now, with a time series plot, our X domain is time, and so talking about trend should have a pretty natural feel to it. Basically, how is our response, in this example, global daily frequency of confirmed COVID-19 cases, changing or evolving across time? Now, just as we mentioned, our response jitters around from one day to the next, especially out towards the right here, but we can describe macro trends, trends over longer expanses of time. So what do we see here? Well, we got a kind of a little upward trend through the last half of March 2020. We got kind of a leveling out here through April into about the beginning of May. Another increase here from about the end of May through July, and another leveling out during August, and another upward trend during September of 2020, and so on. And almost as if on cue, the first macro scale downward trend started about at the new year, turning into 2021. Okay, moving on. Geocoordinates. Now, geocoordinates can be thought of as a special case of a bivariate numerical representation, like we said at the introduction here. Here, we're going to make use of the whole globe, planet Earth, good old terra firma. Now, one nice thing is that our Cartesian space is familiar, or we can make it familiar by indicating familiar features like lakes, oceans, geopolitical boundaries. Another way to say this is that I think we pretty much all know what we're looking at here. Equally obvious is that this surface is two-dimensional, like a poster or a video. Of course, in reality, these familiar features are really etched into the surface of this grand and wonderful big blue marble planet Earth. Planet Earth is closely spherical, not exactly, but pretty close. So question here, how can we project this 3D surface onto a flat 2D Cartesian surface? Well, let's take a look. Let's dive in here. The equator defines something close to a great circle at latitude 0. Lines of longitude here are known as meridians, and these lines run from pole to pole here. So for illustration, we're showing two meridians, 10 degrees longitude and 12 degrees longitude. So if we are on the equator and I'm at 10 degrees longitude, this is in the city of Afakma in Gabon, and you're at 12 degrees longitude around the Avindo National Park area, we would be separated by about 222 kilometers, or about 139 miles, as the crow flies. However, if we are much farther north, say at latitude 60 degrees, and I'm still at 10 degrees longitude, this would be west of Oslo, Norway, and you're still at 12 degrees longitude, this would be east of Oslo, we would be separated by only about 89 kilometers, or about 56 miles. We'd be much closer than when we were at the equator. Now, there are many mathematical projections that cartographers and geostatisticians use to map or translate the 3D surface of the Earth onto a 2D surface. And none are perfect, to be sure. But one very simple and popular way to do this is what we've already just looked at. This is a rectangular projection. Not the most imaginative name, but it's accurate. The map distance between two meridians is the same at every latitude. In other words, a rectangular projection transforms the surface of the Earth so that the meridians are all parallel here. They don't intersect like they do on the surface of the globe of the Earth. This has the effect of horizontally stretching regions that are close to the poles. And to just offer an example here, on our rectangular projection, the area of the continental U.S. appears to be about the same as that of Greenland, which is much farther to the north. However, on the surface of the globe, the Earth, the area of the continental U.S. is more than 3.5 times greater than that of Greenland. Now, we still have yet to look at an example of plotting geographical data, and we're going to leave this as part of our Quant Slob challenge for this video into the next. Now, here we go. The ultimate source of UFO data we've looked at earlier in this series is provided by the National UFO Reporting Center, NUFORC. Now, given the information presented here, first part here of our challenge, do you think we can plot these data on our map? And the second is, if we can, just using our imagination, what do we think the global distribution of UFO sightings might look like? That's it. That's going to do it this time around. Thank you very much for tuning in. Don't forget to stay tuned for more Quant Slob.